Hi everyone, recently I got asked this question. Two spaceships are launched from the same place at the same time in opposite directions, both eventually reaching a velocity of 0.7 c in their respective directions. The technicians at the launch site see both of these spaceships to be traveling away from themselves at 0.7 c in opposite directions. When the second spaceship is viewed from the first, and also vice versa, what would the velocity of the other ship be? Numerically, it would appear that the speed at which either ship is moving away would be 1.4 c from the other. Discuss the validity of this supposition. Okay, so we know they can't be moving away from each other at 1.4 c because that would be putting them at faster than the speed of light. So let's draw a diagram and figure out what's going on. Now, in this diagram, we're going to say that we have the Earth here. The Earth is where both spaceships have launched from. Steve is a technician on the Earth. He's watching all this going on. We've got Pete as a pilot on this spaceship here, moving to the left, the negative direction at 0.7 c. We've got this other spaceship here, moving to the right at 0.7 c. What we want to know is, what is the speed of that spaceship in Pete's frame of reference? The speed of this spaceship in Steve's frame of reference is 0.7 c to the right. What would the speed of that spaceship be in Pete's frame of reference? We're going to have to use a Lorentz transformation to figure this out. As we look at this question, we're going to use Lorentz transformations, which means we're going to be interested in these values or these quantities called u, u prime, and v. Now, for the sake of the Lorentz transformation, we're going to say that v is the velocity of Pete's spaceship relative to Steve in Steve's frame of reference. And that's going to be negative 0.7 c. Negative because it's moving to the left. We're going to say that u is the velocity of that spaceship there from Steve's frame of reference. That's positive because it's moving to the right, and we're going to say that it is moving at 0.7 c. So Pete moving to the left of Steve at 0.7 c. This spaceship here moving to the right at 0.7 c. Both of these relative to Steve's frame of reference. U prime is the mystery value that we're interested in finding out. U prime in a Galilean system would be thought to be the velocity of this spaceship in Pete's frame of reference, and you would think if you were Galilean that it was 1.4 c. We're going to say that that's not possible because that would mean that this spaceship is moving faster than the speed of light in his frame of reference, which we believe is not the case. So we're going to use a Lorentz transformation to try and find out what actually is the velocity of this spaceship in Pete's frame of reference. What is u prime? So as we go to figure out what is u prime, we've got u minus v on 1 minus uv on c squared. We'll plug in our values. So now we've gone and plugged all our values in. We've got positive 0.7 c, subtract negative 0.7 c. So subtracting a negative, that's going to end up being a positive. We've got 1 minus this value here, 0.7 c multiplied by negative 0.7 c. 0.7 times negative 0.7 is going to end up being negative, negative 0.49 c. We've got minus negative 0.49 c. So we'll see what that does. So we end up with 1.4 c over 1.49, which gives us a final value equal to 0.9396 c. So the speed of this spaceship in Pete's frame of reference is not 1.4 c, as a Galilean system might suggest. 1.4 c is faster than the speed of light, and that's not what we think happens. No, instead, the velocity of this spaceship in Pete's frame of reference is 0.9396 c. Using a Lorentz transformation that we can find in our formula and data sheet, and recognizing that v in that Lorentz transformation is the velocity of Pete in Steve's frame of reference, u is the velocity of that spaceship in Steve's frame of reference, and u prime is the velocity of this spaceship in Pete's frame of reference. Okay, I hope that was useful.